Hi everyone, this is it. Everything that we have learned in this chapter about the fundamentals of programming in Go has brought us to this point. In this installment of Programming for Lovers, we're going to implement two prime finding algorithms. A relatively intuitive approach, and then the sieve of Eratosthenes from ancient Greece. How much faster could such an old algorithm be? Well, you're just going to have to join me in this code along to find out. As always, if you enjoy what you see, please like, subscribe, and join our course at programmingforlovers.com. Let's code. So you'll see that I've created a primes directory inside of GoSRC, and then inside of that I created a main.go file, and I've started to fill that in a little bit just with an FMT print statement saying that we're going to find primes, and I've also filled this in for your sake with some pseudocode that we have from our core text. So you'll see that the pseudocode that we're going to need is going to be the trivial prime finding algorithm pseudocode that's going to take an integer n, and it's going to return an array containing n plus 1 Boolean variables where everything's going to start off as false, and then we're going to range through and check, is the given index prime? And if so, I'm going to set prime booleans of p equal to true. So it's going to contain a record as to whether or not each given integer is indeed prime. So the good news about this code along is that we've essentially done everything that we need to do in order to implement the trivial prime finding algorithm, and then we're going to implement the sieve of Eratosthenes too. So we can just simply start coding. We've got our pseudocode, we know all the basics that we need in order to implement these algorithms, so let's do it. We're going to start off with our trivial prime finder function. It's going to take as input an integer n and returns a slice of Boolean variables, storing the primality of each positive integer, I should say non-negative integer, up to and including n. Okay, always good to establish that function comment. And I'm going to call it trivial prime finder. It's going to take an integer n as input. As I said, now we get to practice what we've learned about previously about how slices work. And I'm going to say we're going to have a slice of Boolean values or variables. And that's what I'm going to declare. So I'm going to call that prime Booleans. I can scroll this down a little bit and we can see our pseudocode. I'm going to use our one-line declaration. I could use a two-line declaration for creating a slice. Remember to declare a slice of length n plus 1. We're going to have a make command, and then we're going to indicate that we want a slice, and we need to tell it the length of the slice that we want. Down here, that's eventually what I'm going to return. So that array is going to store whether or not each non-negative integer is prime or not. And so then we're going to have a for loop that's going to range this integer p from 2 to n. So that means I'm going to need to have my initialization step there, setting some variable p equal to 2. I'm going to perform the actions within the for loop for as long as p is less than or equal to n, and I'm going to increase p by 1 each time. So because our slice has length n plus 1, we know that its indices are going to range from 0 up to n. So we could have it up to and including n, or up to but not including n plus 1. It's going to be up to us. I like, because we're thinking about p as an integer and taking different values, it's going to go from 0 up to and including n. I like p less than and equal to n in this particular case. And then within this for loop, we're going to check, is it the case that when we call a subroutine IsPrime, that's going to return true if p is prime and false if it's not? Is that true? Then we're going to set prime booleans of p equal to true if so. And we can make a couple of simplifications here. I mean, this is following our pseudocode, but I would point out, well, for one, IsPrime of p is going to simply return true or false. So we don't actually need to check whether or not it's equal to true. If it's true, then we're going to enter this if block. So that's one short simplification. If you like writing your if statements the other way, if IsPrime equal to true, that's fine too. One other additional simplification I would point out is that technically we're just setting prime booleans of p equal to whatever IsPrime of p is in any case. So we're always going to call this subroutine IsPrime, and if it's true, we're going to set prime booleans of p equal to true. If it's false, it's already false, but really we want to set prime booleans of p equal to whatever IsPrime is telling us. So I don't technically even need an if statement. I can make this little optimization here, and I wouldn't expect you again to see that immediately, but I'm just pointing out it's a way of making our code just a little bit shorter to set prime booleans of p equal to IsPrime of p. And so our function is nice and short here. It's very concise. We just have one for loop, and each time through the for loop, we're just calling a subroutine. And as we go through the course, you're going to see that this is a strength, not a weakness of the way that I'm going to try to program, because having nice, short, intuitive functions that call subroutines is going to make functions that are easy to test and easy to work with and easy to understand. So once we have that function, we're now ready to write our subroutine, which is IsPrime. And remember, IsPrime is going to take as input an integer, let's call it p, and it's going to return true if p is prime and false otherwise. Note that we didn't start at 0 and 1 because 0 and 1 are certainly not prime in this for loop. So I'm going to, when I declare this array, I get default false values, which is what we want for those two. So I don't need to start this at p equal to 0. I'm going to start it at p equal to 2. Returning back to IsPrime, our function signature is going to be func IsPrime pint, and then it's going to return a Boolean value. So we need to tell it to return a Boolean. If you want to take a look at our subroutine, our pseudocode, I should say, and recall how this works, we started actually with checking every integer k between 2 and p minus 1. And then we realized we have a simplification. We actually only need to check the potential divisors k of p between 2 and root p. And if I have not found any divisor of p in that range of integers, then I can conclude that p is prime. If I ever find one, I'm going to immediately return false. So I'm going to know that k is indeed a divisor of p, and I want to return false. So this is, again, just another for loop. And here it's a for loop with an if statement inside of it. And so I'll have a function here, which is for k equal to 2. And if we want to check, one thing we haven't done thus far in the course is use a square root. Now, fortunately, that's going to be built in for us. So we've got a square root function that's going to come from the math package in Go, and I can access that in the same way that I access the FMT package. So when I print a statement in Go, I have fmt.println. And if I want to access this function square root from the math package, I'll access it with math.sqrt. So I want to do this for as long as k is less than or equal to math.square root of p, and each time I'm going to increase k by 1 each time through the loop. I'm then going to say, well, is it the case that k is a divisor of p? And if that's the case, then I want to return false. I can conclude that p is composite. So I'll just say, is k a divisor of p? If so, return false. Good to have a nice comment there. And so to check that, I'm going to use our percent operator and take the integer division of p by k and check whether or not the remainder is 0. So if it's the case that p%k is equal to 0, then I know that k is a divisor of p, and I'm going to immediately return false because it's composite. If I survive all of these checks, then I know that p is prime. So I can simply, at this point, return true. And this is something that we'll see throughout programming, is a lot of times you'll have to range through a lot of different values and check something. And if any of those conditions is true, then you might return either true or false. And if you survive all of them, then you return the opposite. So that's our IsPrime function. And I wanted to write it in this way and save and compile. So down here I've got a terminal open and I'm in my Go directory. So I'm going to cd into src primes, go build, and I'm not going to be able to run this yet because I'm going to get a compiler error. And the compiler error that I'll get is, well, a couple things. One, if we look at the math package, it's going to tell us that the square root function needs to take a float 64. It's going to take a float 64 as input, and it's actually going to return a float 64 as output. So after it returns, this is going to be a float 64, and I want to compare that to k. And so I'm getting a couple of compiler errors on the same line. One being that I need to give it a float as input, and the other that when this comes out as output, I need to make this comparison as a float here and a float here. So I'm going to cast, this is a concept that we learned about earlier in the course, I'm going to cast those variables to float types. It's not changing the underlying type of k, it's just checking, doing this comparison, assuming that k were a float. So it's switching its type sort of momentarily here. And that's going to hopefully allow us to compile this now. And now that we know that our functions compile, we should be able to go in and run this code on a sample n. So we can go to our func main and set some value of n. Let's set n to be 10, for example. And I'm going to print whatever the result is of calling TrivialPrimeFinder of n. And so now I'm going to make sure to save my code. I'm going to go build again. I don't get any compiler errors. And now I'm going to run primes. And we can look at our slice that was returned. It has length 11. And make sure that it makes sense. So 0 and 1 are not prime, certainly. So those should return false. 2 is prime, and it returned true. 3 is prime, yes. 4 is composite. 5 is prime. 6 is composite. 7 is prime. 8 is composite. 9 is composite. And 10 is composite. So we need to test our function more, but it seems like it's behaving appropriately for now. And we have our first prime finding algorithm written. The next thing to do would be to implement the sieve of Eratosthenes. And then we want to compare these two approaches by timing them and seeing, is it the case that the sieve of Eratosthenes is faster? If so, how much faster? And so we can take a look at our pseudocode for these two algorithms. I've got these, the sieve of Eratosthenes pseudocode below. It's going to rely on a subroutine as well. And how is this going to work? It's going to, again, create an array of n+1 Boolean variables. And in this case, I am going to set everything to initially true. So if you follow the main text and our explanation of how the sieve of Eratosthenes works, it sort of assumes that everybody initially starts off as true, and then it takes the smallest prime number that we know of, and then it crosses everything off that is a multiple of that number. So for that reason, we won't start everybody as false. I will start prime booleans of 0 and 1 as false because we know that those two numbers are not indeed prime. And we want 2 to start off as prime. And then from that point forward, we're going to assume 3, 4, 5, 6, 7, 8, 9, 10, all those numbers are prime. But something like 4, 6, 8, and 10, those are all going to get crossed off when we consider all the possible multiples of the number 2. So we're going to range through and successively, starting with p equal to 2 and ranging up to the square root of n, at each step of this algorithm, we're going to say, is it the case that that number is indeed prime? So has it survived thus far? And if we know that it is true, prime booleans of p is true, then we're going to cross off its multiples. So we're going to cross off 2 times p and 3 times p and 4 times p and all the possible multiples of that number up to n, which is how the cross off multiples subroutine is going to work. It's going to take our Boolean array containing the primality of all the integers up to n, and it's going to take the integer whose multiples we want to cross off, and it will find what n is. So if we know that the length of the array is equal to n+1, then we can get n by taking the length of the array and subtracting 1 from it, just doing a little bit of algebra there. And then we're going to consider all the possible multiples of p between 2 times p up to n, and we're going to cross them off. So we're going to set prime booleans of k equal to false. And then at the end of this process, we're going to return prime booleans. And that's just going to cross off just the multiples of p, but we're going to continue doing this for everything that we find that is prime. All right, that was just a quick review of how that algorithm works. And I'm going to copy my comment here. And I'm just going to change that comment to sieve of Eratosthenes. And I'm just going to say as well, implementing the sieve of Eratosthenes algorithm. So our function signature is going to look pretty similar to the TrivialPrimeFinder. I'm going to take an integer n, and I'm going to return a slice of Boolean variables, which is what we want. And I might move up my pseudocode here so I can see it. Let me do that. Just so you can see it as we go through it. So you see I'm not doing anything that's going to be tremendously different here. Again, I'm going to declare a slice, that is a Boolean slice of length n plus 1. Again, at the bottom, that's what I'm going to return. And prime booleans of 0 and 1 start off as false. So we know that they're false by default. And now set everything from 2 onward equal to true. So I'm going to have a for loop where some variable p is going to start at 2. It's going to go up to the length of the array. So it's going to go up to and including n. And we're going to increase p by 1 each time. And I'm simply going to set prime booleans of p equal to true each time. And so that will handle these first 3 lines of our pseudocode. Then it's a matter of doing a separate range where I'm going to say, consider every possible integer p but from 2 up to the square root of n. And as I go, if prime booleans of p is true, cross off its multiples. So I'm going to have a separate for loop. Remember that the scope of this variable p here is within the block of the for loop. So I'm going to use the same variable, and that's going to be okay because these variables are going to have separate scope. So we're going to go between 2 and now math.square root of n with p increasing by 1 each time, except remember that we need to convert our n to a float, and then we need to do our comparison as floats too. So I need to convert p to a float here too. Now I make the check, is it the case? Is p prime? If so, cross off its multiples. I like saying the same thing over and over again. I hope you don't mind. But it's good for repetition just so we're 100% clear what we're doing. And I even suggest maybe even talk yourself through code as you write it. I find I become a stronger programmer when I sit alone and talk to a camera about how to code. If prime booleans of p is true, then we're going to cross off its multiples. So I'm going to set prime booleans equal to cross off multiples, and I'm going to give it the prime booleans slice, and I'm going to give it the integer p whose multiples we want to cross off. And that's it for this function. I've passed all of the work of this function in terms of doing the crossing off to a subroutine. Now it just is a matter of writing that subroutine. And I can say cross off multiples. How is it going to work? It's going to take as input an integer p, and it's going to return, it's going to take more than an integer p, it's going to take a Boolean slice prime booleans, and an integer p, and it's going to return an updated slice in which all multiples of p greater than p have been set to false. And to be more precise, I guess I should say it's all variables in the array whose indices are multiples of p. Okay, it's very technical, but there's nothing wrong with being precise. So I'll say func cross off multiples. And then I'm going to take my prime Boolean slice. Remember, its type is a slice of bools. And it's going to need to take an integer p also. And then it's going to return an updated slice. So the return type is a slice of bools too. And then we could look at the pseudocode and say, again, refresher of how this works. It sets n equal to the length of the slice or array minus 1. And then it's going to do this ranging where we start k at 2p, not at p. We don't want to cross off p if p is prime. We're going to start at 2 times p up to n and simply set prime booleans of k equal to false. So to do this, we'll set n equal to, we're going to use the len keyword and say that n is equal to the length of prime booleans minus 1, since that length is n plus 1. And way down here, I'm going to return my slice. And then in the meantime, consider every multiple of p starting with 2p and cross it off by setting its corresponding entry of the slice to false. So here's where we have a chance to practice what we have seen with for loops that don't just follow the form, setting some variable equal to some integer, often 1 or 0 or 2, and going up to some value and then increasing by 1 each time. That's a very, very common type of structure when we program, but this is an example of where we might use a for loop that's a little bit different from this, because if I'm considering all multiples of 5, for instance, I don't need to consider a value like 9, because that's not a multiple of 5. I only need to consider the values that are indeed multiples of 5. So how I'm getting at that is to say, all right, well, that means that we're going to start a value, say k, equal to 2 times p. Remember, Go is not going to like it if we say 2p. We need to say 2 times p. K is going to go up to n, and it's tempting to write k++, but each time through, we're going to increase k by p. So again, if p were 5, the first thing we want to cross off is 10. It's already been crossed off, but we were going to cross it off anyway. And then we would cross off 15 and 20 and so on. So every time through, we would add by 5. And in general, if you're considering some integer p that you're crossing off its multiples, we just need to increase k by p each time. So we need to set k equal to k plus p each time through the loop as this post condition. We also learned, again, practicing everything that we've seen about the basics, that we have a shorthand way of writing this. So if we want to add p to the value of k, we can use k plus equal p. Right. And now it's just a matter of saying, let's cross it off. So the current integer index that we're interested in is k. So we're going to set prime booleans of k equal to false. And that will handle all the crossing off. And at the end of that, we're going to return prime booleans. So we've implemented the sieve of Eratosthenes too. And the first thing I should do probably is save, compile, and everything compiles. And then actually, let's go and make sure that we get the same output. So let's make sure that the output matches here. And I'm going to call sieve of Eratosthenes with an input of n as well, and that's the same n. And I'm going to save that and compile and run. And I would hopefully, knock on wood, this is a wood desk, hopefully this is going to match, and we see that indeed it does. So we have the same faith in Eratosthenes' algorithm that we do in our TrivialPrimeFinder. And then it's just a matter of doing a couple more things. One, this tells you where the primes are, but it's not satisfying for somebody who wants to know the primes. I've got to go through and say 0, 1, 2, 3, 4, and check each one. So one thing that we might do is instead have a function called, like, say, list primes. And that's one more function that I've provided here in terms of pseudocode at the bottom. That function is going to return a list of just integers. I've got a cough incoming. We're going to see if I can hold it off. I could not. I failed. It's going to return a list of integers. So we're going to start this in an array of integers as having length 0. And then I'm going to give you a hint that sieve of Eratosthenes is faster than our trivial prime finding algorithm. So let's just use it as a subroutine. And that's going to grab that Boolean slice that we're interested in. And then I'm going to convert that Boolean slice to an array of integers. So I'm going to range over it. And I'm going to say, is it the case that prime booleans of p is equal to true? And if so, then I'm going to append the current integer I'm looking at to the list of primes. So this is a pseudocode representation of adding to the end of a slice or end of an array a value that we're interested in. I want to point out, we don't actually know in advance exactly how long this list of primes is going to be. If I give you n equal to 1,000,000, could you tell me exactly how many primes there are up to 1,000,000? No, there are good bounds on this with the prime number theorem. That's going to be more math than we want to consider. So I want to point out, just in general, this is a way that we will often write code when we don't know in advance how long a list or an array needs to be. We're going to create it to have length 0, and then every time we want to add something to it, we're going to append as appropriate. It's going to be my cough suppressant. A little sip of water. So let's convert this to Go. And say, let me move my pseudocode up too in case you just want to see it while I'm coding. So we have our list primes. But it's going to be a pretty short function. Really, all we need to do is know what the append notation is in Go. But I'll say, what is it going to do? List primes takes as input an integer n, and it's going to return a slice containing all prime numbers up to and including n. I should say possibly including n. N might not be prime. So our function signature is going to be func list primes, n as our input integer, and here it's going to return a slice of integers. And what I will do is first create a slice of length 0. And we know how to create a slice of length n. Creating a slice of length 0 is going to follow the exact same syntax. And so I'll set prime list is equal to make a slice of integers of length 0. Eventually, that's what I'm going to return. I'm going to return my prime list. And I'm going to call our fast algorithm. So I'm going to say prime booleans is equal to whatever we get when we call the sieve of Eratosthenes on n. And now we're going to range through. So note, for every integer p from 0 to n minus 1, that's going to range over all of the variables in our prime booleans array. So if we're ranging over everyone, let's use our range keyword that we learned about in Go. Another thing that we can practice about Go syntax. So I'm going to say p colon equal to range over prime booleans. And is it the case that prime booleans of p is true? If so, append. So if prime booleans of p is equal to true, remember, you can have that equal true if you want. You don't have to. You can remove it if you like to. And if that's true, then what are we going to do? Append. So prime list, you might wonder, what's the Go syntax here? It's simply equals the append operation, and the append operation is going to take two things. One, the list you're going to append to, and two, the item that you want to append to it. So it's the exact same notation as what we have on the level of pseudocode. And that's it. This is a short function because we've already done the hard work. The sieve of Eratosthenes is going to be the engine for figuring out what's prime. All this is doing is going through and ranging through that prime booleans array and identifying what's true and figuring out what those integers are. So I will save this and make sure it compiles. Indeed it does. And we can call this too. So let's call list primes of n. And make sure that we list out the primes up to and possibly including 10, 2, 3, 5, 7. I could change this to 11. Hopefully we'll pick up 11 too. And indeed we do. So the algorithms appear to be doing hopefully the right thing. And now it's just a matter of timing them. So we're going to have our final answer here. Is the sieve of Eratosthenes really that great? And so let's see. In order to answer that question, we're going to need our code that we've used in a previous code along for timing an algorithm. And so the other thing I'm going to need is to make the value of n larger. So what I'm going to do is I'm going to set n equal to, let's start it at not 1,000, not 10,000, not 100,000, but 1,000,000. Let's start it at 1,000,000, because the other thing that we've learned is a lot of times with algorithms, you start to see one algorithm really start to beat another algorithm at scale once the data start to become large. So let's start n equal to 1,000,000 and see what happens. You'll also maybe recall, if we want to time algorithms, we're going to need some packages. So in particular, I'm going to need the log package, and I'm going to need the time package. Those are not bright orange because I haven't used them yet. But I want to start a stopwatch, and I want that stopwatch to be started with this time.now command. Then I'm going to call TrivialPrimeFinder of n. I don't need to print it or anything. I'm just going to run that function, so it will run behind the scenes. And when it's finished, I want to stop the stopwatch. We saw this with GCD algorithms previously. So I'll call time.since, give it the start variable as input, and then the elapsed variable is now going to know how much time has passed. And then I'm going to log this and print it to the console and say that TrivialPrimeFinder took, to format the time, we use %x. Then we're going to have a comment, and I'm going to say elapsed. We're going to use that same code, except I'm going to have different variables, start and elapsed. I'm going to change them to start2 and elapsed2. So I'm again going to start the stopwatch. I'm going to call that start2. And then I'm going to call the function, and I'm going to call that elapsed2. Make sure you change this to start2 also, otherwise it's going to seem like sieve of Eratosthenes is slow since we were using that start of the stopwatch. Make sure you change that too. And then I'm going to print a statement to the console about how long it took. So we'll say sieve of Eratosthenes took, how long did it take? Elapsed 2. Let's not print a list of primes. And so I'm going to comment that out. And now this is just going to time the two algorithms and do nothing else. It's not even really going to print anything. Maybe to do that, I'll say, well, we'll know when it's complete because it'll be printed. So I don't even need another print statement. Let's compile. Make sure you save first. And then let's run. And we'll see what happened. We already see a speed up. TrivialPrimeFinder took 52 milliseconds, so 52 thousandths of a second. 53 if you round up. And sieve of Eratosthenes is a little less than 50 times faster on this input. So it only took a little more than 1 millisecond in order to find primes up to n equal to 1,000,000. So that might not seem so great. But again, if you followed our discussion of GCD algorithms, what we saw is, in that case, the larger you make the input data, the more the divide, the more the ratio between the runtimes of the two approaches. So let's see if that, what I said is often a seminal principle in algorithms, let's see if that is true here too. So I'm going to add a digit. Let's go up to 10 million. I'm going to save. I'm going to compile, and I'm going to run. And now you saw that little delay, because when I increased by a factor of 10, TrivialPrimeFinder is now up to 1.2 seconds. sieve Eratosthenes, now quite a bit faster. You saw that here it increased by a smaller factor. So it's now at 17 milliseconds. So the gap is starting to increase. And if I make this 100 million, well, then what is going to happen is I'm really going to have a wait. And we can just wait and see what happens. I increased the input here by a factor of 10, and the trivial prime finding algorithm is ranging up to n. So you might think, well, is it going to be about 10 times slower? It'll be a little bit longer than that, because calling IsPrime on these larger and larger numbers is really going to drag it down. So I'm sitting here waiting on TrivialPrimeFinder, and I'm not really going to have as long of a wait on sieve Eratosthenes. We're going to see. So you see how fast that was, that it took forever. I needed to kind of fill time because TrivialPrimeFinder took half a minute, took 31 seconds. Sieve Eratosthenes is still very fast, still less than half a second. It's at 498 milliseconds. So it's found all of the prime numbers up to 100 million in under a second, which is pretty cool. And I say, not too bad for a 2,300-year-old algorithm. That's it for this sequence of code alongs. If you made it this far, I'm impressed. I'm impressed that, for one, you should be proud of yourself and that you've made it this far and you've learned this much about programming and programming in Go. So give yourself a pat on the back. Number two, I'm impressed that you managed to listen to my voice for this long. I don't know if I could tolerate that. So that's another matter, though. And so I think you've done great and you're ready to start implementing some algorithms on your own, practicing what you've learned by seeing some exercises that are going to get you to apply what you've learned in new contexts. So that's where I'm going to leave you, by encouraging you to do some exercises that we're going to provide with the course. And I hope you have fun with those. And I'll see you in the next chapter. But until then, happy coding.